Thanks, Tom, for inviting me first of all, and thanks to everybody for coming. Yeah, I don't take for granted anymore the experience of an in-person talk. So it's good to be back with that. So before we start, a lot of acknowledgements. I'm not going to go through all of them, but there is definitely two people I need to thank. It's Zoran Cvekovic and Hussein Ajibaboglu at King's College and Meta University in Turkey. A lot of the work that I'm going to present today is work that I've done with them, and also these slides, they're actually they're coming from, some of them at least, a good percentage, they're coming from a tutorial that was given a couple of years ago at ICASP. So I would like to thank them. And then there is a number of people, I'm not going to go through all of them, but as I said, the work has been, that I'm going to present, parts of it have been done with a lot of people. So yeah, thanks to all of them. As I said, the scope is, I'm thinking about applications within VR, MR, and AR. Right, we call them together XR. It's the term that encompasses all of them. But essentially, they go from VR, right? So you're immersed in a world that is all virtual, whereas virtual reality and augmented reality, they're both a mix of real reality and what we call virtual elements. What we call mixed reality is a halfway case where you also interact with the virtual elements. Okay, but I feel like maybe this distinction is a bit, it's a lot more blurry than it is between VR and MR, AR. The other application case I think about is often computer games. So it doesn't need to be necessarily you feeling immersed into the world. But this is the scope. This is the applications that we're thinking about. And as you can imagine, we're all here. We're interested about audio. The question is, how do we render the audio of these virtual elements? Right? There is a turbine here, for instance. It's going to have to make some certain sound. How do we render it in a way that feels natural, that feels like there is actually a sound source there? Right? It needs to be externalized. It needs to be outside your head, not like with headphones, everything inside your head. And it needs to be feel natural. We're going to talk about what we need to do to make that happen, hopefully. Just to say a little bit more about that, so imagine, for instance, a VR application, right? I want the person to feel immersed into a virtual scene with a number of objects, and the actual person is somewhere else wearing headphones and VR goggles, perhaps. And in order for the person to feel in that position, we need to do two things. One is to synthesize the room acoustic of the space, to model the room acoustics of the space. And the other is, we could call it oralize, to make that sound audible. And this corresponds, for those of you who are familiar with it, it amounts to rendering, for instance, binaural audio. How to render the room acoustics in a way that does sound like you're in the room. And this is the VR case, right? But also in MR, AR, it's the same thing. But the difference is that the virtual and the real space, they're overlapping with each other, right? So I could have, for instance, Hussein and Zoran that are presenting with us together. We're all wearing AR goggles, and we want to render the room acoustics of this space, in that case, and then render their voices as if they're in the room with us, right? So the problem is essentially the same. With some subtleties, but at least from our point of view, I'm thinking about both applications, and this is what we need to do. Okay. Just preamble, I like to be interrupted, right? If I get interrupted, it means people are engaged, and just ask questions. You can raise your hand also during, I don't mind. Okay, hopefully we're just gonna go to time. I have 33 slides, but it usually takes me 3 or 4 minutes to go each one of them. So we may take 2 hours, but no, I'm just kidding. All right, so why do we need to render the room acoustics? Okay, so the other part about binaural sound, it's maybe more familiar, but why do we also need to render the room acoustics in all these applications, in VR and AR? Well, it turns out that we're accustomed to perceiving room acoustics, right? We unconsciously doing our entire life. Right? So when that is missing, then things don't work, right? So, and I'm not just talking about echolocation. If you've ever heard of the fact that people with visual impairments, they can locate their position in a space by making sounds, for instance, or clicks. I'm not talking about that. I'm talking with all of us, we're accustomed to be perceiving room acoustics. And when it's absent, we notice, right? If you go into a very reverberant room, you're like, oh, or if you go in an anechoic chamber, for those of you who had the luck to go in an anechoic chamber, it sounds odd, okay? So that's where this is coming from. So we're accustomed to, and there are a number of things that we don't realize, but we essentially, if you don't render room acoustics, bad things happen in these applications. First of all, it's a lot more harder to make you feel the sound is externalized, meaning everything is going to be inside your head if you don't render room acoustics, right? So whatever virtual element is not going to sound like it's here, it's going to sound like it's inside your head. So adding room acoustics really helps with externalization. It helps with immersion, realism and presence, spaciousness. Another important one is source distance, for instance. We normally use two cues to estimate source distance. One is their loudness. If we're familiar with, I don't know, how a human voice should sound like, we use loudness for that, and that is fine. But then we also use what we call the direct to reverberant ratio, how much energy is coming from the sources, how much energy is reflected from the room to estimate distance. So in applications like this, it's important also to have that cue present, and that means you need to render room acoustics. And also source width of a certain source, okay? So then we need room acoustics. I hope I convinced you. How do we do it? Well, there is a large number of room acoustic models that have been developed over 50 years. I nearly have no time to go in 1% of them. So there are some, by the way, I can share the slides. So at the end of the slides, I have references. These are a couple of papers by Vesa Valimaki and others. Aptly called 50 Years of Artificial Reverberation. I strongly recommend these papers. But just very briefly, we can maybe classify them into three parts. One is measurement based, right? I go into a room, I measure an impulse response, which is what a lot of people would naturally do. That is a little cumbersome in some cases. In AR, you don't know if you're gonna be exposed to a room that actually matches one of your measurements. And the same in computer games or in VR, etc. So it's cumbersome. They're also often quite computationally complex because convolution, it's not a simple operation. At least the ones that we're going to talk about are simpler than convolution. The other class is physical-based models, right? I take the wave equation, I try to discretize it in some way, shape, or form. And spatial discretization and either time or frequency, so we can solve it numerically. And that is a very elegant solution. But the problem is that it has comparably high computational complexity, so we don't want that. And there are some GPU-based implementations that are quite promising, but still at the moment, they still remain costly. Okay. The alternative, okay, there is also geometrical acoustics models, like if you've ever heard of ray tracing or the image method. They have lower computational complexity, but also lower accuracy. Essentially, they do approximate the wave-based models by making the assumption that sound travel like rays. But still, for the application we're thinking about, they're probably still high complexity because you would still need to calculate an impulse response and then use a convolution. So the methods that are more promising for this sort of applications are delay network-based models. And this is what I'm going to talk about for the rest of the talk. So these are methods that don't model explicitly the physics of room acoustics, but they try to approximate it with something that is convincing, perceptually convincing. And they have very low computational complexity. So we're talking much lower than that convolution. It's just, we're going to see it's just recursive IIR filters for those of you who are familiar with that. The disadvantage is that there is essentially no physical accuracy and no explicit modeling, okay? But there is some that are halfway, which is what I'm going to be talking about a lot today. Yeah? Yes?
I just wanted to respond to what you just said.
Yeah.
I'm doing a lot of real measurements and modeling.
Yeah.
Acoustics and vibration.
Yeah.
And it's definitely completely no physical accuracy anyway.
Right.
Even the measurement itself could be tricky.
Yeah.
But trying to ray tracing model or sound-based model still don't have accuracy.
Yeah.
So it's no point of spending so much
Right.
computational time for something which is not accurate anyway.
I agree with you. Thanks for noting that. And one thing that it's particularly difficult is also to make these models to match the real measurements, right? It's because the models are just different, right? So I agree with you. Yeah. Okay. So now just thinking back about the scope of applications we're thinking about, AR, MR, VR. We need low computational complexity, right? Imagine in AR glasses, you have very strict battery requirements on it. So this needs to be extremely fast, right? You can't occupy a large portion of your CPU with this. We'd like it to be as accurate as possible, either physically or perceptually. We can't do physically probably, but perceptually maybe we can. And ideally, and this is maybe my addition, but you'd like to set the physical properties of the environment explicitly. So, for instance, in computer games, you have the texture of the room, you know the size of the room, you know where the observation point is and where the source is. So you know more or less what is it that you would like to set. So you probably want those parameters rather some other parameters like how much reverberation there is, for instance. Okay. So within this class, maybe geometrical acoustics to a certain extent and delay network-based models are the most appropriate. And that's mainly because the wave-based models have, at least for now, they still don't satisfy this low computational complexity constraint. So let's start with a little bit about delay network-based models. And this is a very typical approach, is to essentially to use separate models for what we call early reflections and another module for late reverberation. Right? The early reflection, if you think about my voice at the moment, I'm talking and there is maybe some reflections off the floor. That's usually pretty strong from the sides. Maybe a couple it doesn't need to be what we call first order only. It can also be second order, that they reach you, they have higher energy and they're more sparse in the time domain. If you take an impulse response measurement, you can pretty clearly see them. And then in an impulse response, they start to add up, so the density starts to increase so much that it essentially becomes almost like exponentially decaying noise in an impulse response. Okay, and these two things, they're quite different. A typical approach is to treat them differently in this sort of models and to have some delay lines that model the early reflections. They may be filtered by the absorption of the wall, for instance, or if you want to render using binaural audio through some head-related transfer function. Whereas the late reverb is generated differently using, for instance, a recursive network that creates something that is not necessarily related to the echoes precisely themselves, but they just generate that lush and noise-like tail to the reverberation to essentially model what we normally observe in typical rooms. So these are the properties that we like about late reverb. It needs to be a smooth decay, very high echo density, smooth frequency response. We don't want it to sound metallic, so that means we want this thing to be a system that has a large number of resonances, that it just behave statistically, but they're not well separated. Otherwise, it sounds quite metallic. That's what the effect is. And one option is what we call more as ideal reverb. A very good late reverb is something that looks like exponentially decaying white noise. Okay, so it's pretty easy to generate, right? We could generate and then run a convolution, but then again, we want to avoid convolution because it's just more than we want to have. So essentially, one idea is how can I generate this exponentially decaying white noise, but without generating an exponentially decaying white noise. And one of the most popular way to do this is called feedback delay networks. So this that you see here is the system diagram of such a system. You have an input here, an output there, and then this gets the input, which could be me speaking, for instance, at the moment, gets multiplied by certain coefficients, then it gets delayed by a certain number of samples, and then it's fed back through what we call a feedback matrix, which is fed back onto itself. You see, this is the recursive part of the filter, and then each part is then multiplied by a certain coefficient added up to the output. I don't know if any of you have been exposed to what we call a state space model by any chance? Nobody? Okay. Well, those of you who have, this is exactly a time domain state space model, but instead of having one top delays here, it's longer, right? So that's essentially what it is. And this generates, so this has been, it's a generalization of Schroeder, reverberator, Stottern, and Pouquet. I know that Pouquet has given a presentation a while back, it might be it. And then it was refined by Jean-Marc Drott and Kagne. And also Sebastian Schlecht has done some very significant advancements lately. I didn't want to present it here because I don't think we had time, but there are a few papers, including this one here, that are excellent. Okay, so this works if you set the parameter delays in a certain way. So usually you use them as co-primes. These weights, you need to make them a little bit of variability, and then having a feedback matrix that has certain properties. Usually we like to have this feedback matrix to be a unitary operation upon which we add some absorption on it. Anyways, it's quite a good structure to generate this exponentially decaying white noise. So it's been quite successful. Just starting to talk now about new stuff, I suppose. So this has also been extended to coupled volumes acoustics, right? In the applications that we talked about, at least so far, we're thinking about a single room. But if you're dealing with VR, AR, MR, hi Stefan. So you also need to deal with more complex architecture, more complex geometries. And I would say that the simplest one and most relevant one that you can think of is that one of coupled volumes, right? And so Orchisama Das and others, she's extended the FDN to what she called a grouped feedback delay network, where you take your scattering, your feedback matrix here, you take it as a block matrix. And then I'm not going to go into the detail of that paper, or actually of any paper. But if you do the design properly of these quantities here, you can obtain what we call the double slope the decay in the room. How many know what the energy decay curve is, by any chance? Okay, thank you, Stefan. Okay, so I mean, what this means, this characteristic here, without going into too much detail, tells you. So on the x-axis you have time, on the y-axis you have the magnitude of your impulse response. And if you have one room with similar materials around the room, the decay that you see is linear, meaning because we're using a logarithmic scale in dBs, that means exponentially decaying. Okay. Now, as soon as you use either materials that are very different or you use coupled volumes, then you start to see a non-linear decay. And for instance, in this case, you see what we call a double slope decay, something that decays faster in the beginning and then more slowly. And this is something that we can perceive, right? There is not with this huge accuracy, but we can perceive it. So it's important that if we want to model coupled volumes with these things, it's important that that effect of double slope decay is there. So that's a paper in 21. I think this is the Dafex paper, but I think she published a transaction paper. And then more recently, a paper is under the revision at the moment, another transaction paper. We extended that to also be able to model the frequency-dependent coupling that exists when you use a small aperture. Right? So on this plot, which is admittedly quite small, you have, for instance, how the coupling between two rooms, right, and this is what we've done in terms of modeling that frequency dependency that you have when you have two rooms connected through an aperture, right? So the coupling between one room and itself, it's at least we consider it to be flat, and then the coupling from one room to another and back, we use a very simple model with a notch filter that model to some extent how sound diffracts inside an aperture. So just, as I said, I'm not going to go into mathematical details. For some, maybe I hope it's a good thing, right? To just look into the paper if you're interested, sort of thing. Okay. So, yeah, what else did I want to say here? Okay, now because I zoomed, I can't move. Okay, so another approach that also counts as delay network models is what we call a digital waveguide network, right? So digital waveguide network were introduced by Julius Smith back in 1985. I think was he your PhD advisor? Okay, yeah. These networks have been used also for musical synthesis, so extremely flexible. But they're also quite useful. I can't remember if it was actually the first application that Julius intended for this thing, to generate that lush reverberation tail. Okay? So the way it works is, imagine a diagram like this, where you have an input, again, imagine my voice, and then you want to observe the output at some point, for instance, your ears. And these are connected through some delay lines that are all interconnected together. Okay, so for instance, there is a delay line here that delays the signal by 107 milliseconds. Then it reaches here, it's delayed to 37 milliseconds, and then back onto itself. And these are all bidirectional delay lines between them. Okay? Now, the operation that happens at this, which we call scattering nodes, is a linear operation. So what you do is you take the inputs at every sample, you stack them onto a vector from all the incoming delay lines onto that node. And then you essentially make a weighted summation of each of these inputs and output them in another stacked vector here, going into all the other directions. So it's a linear operation, simplest operation you can think of. That is described by this, essentially vector equals matrix time vector. And all the weights that describe to each delay line outgoing, how do you weight the inputs, all those weights, they're containing what we call a scattering matrix. Okay? And now, one very cool result is that we're going to come back to this in a second. But the cool result is that if you choose appropriately that scattering matrix, those matrices that contain all these weights, with this form, which we call the Householder reflection, Householder transformation, then this network of delay lines takes meaning, physical meaning. It becomes a model of acoustic tubes, right? It's just something really cool, I feel. If you imagine that you have some acoustic tube that get connected to this place where essentially all the energy goes in all directions, and then you stick your head inside one of these acoustic tube, then this is exactly, well, with some approximation, is what you would actually hear inside the network of an acoustic tube that looks like that, which I think it's quite cool. Okay. Are there questions so far? Okay. All right, cool. So the question is, how do we choose these delay lines? Right? We could choose them at random for them to be co-prime, like it's so often done in FDNs, for instance. And also, how do we choose the scattering matrix? How do we implement absorption into this thing? And this is like a very flexible structure where you can make all those decisions. But I would like to try to introduce one way to do this that is related to the physics of an actual room. Okay. So this is the last part of the talk, but it's going to occupy a lot of the time. These models, we call them scattering delay network. And I would like to so look at this diagram. This is, imagine it's a room seen from above. And all these solid lines here, they're the same that you saw in the diagram before. They're bidirectional delay lines. If we choose the scattering matrix here to be Householder transformation, to take the minimum of acoustic tube, everything is the same. So their length here, I'm not explicitly, their length in time in terms of number of samples is related to the distance that you see in this room seen from above, right? So you calculate your speed of sound and you see, okay, is this 2 meters? Then you calculate what is the delay of that delay line for essentially the delay that you need to assign to that delay line. Okay? And then you have here, I'm also showing a source and a microphone. Imagine my voice and your ears, for instance. And I'm also using some delay lines that in this case, these ones are monodirectional, and they just inject the signal into this backbone network of delay lines. And the observation point is connected also by monodirectional delay lines that just pick up what is the acoustic pressure in each of these scattering nodes and then adds it up into the microphone. Okay. All right, so something else, the position that you see here, I didn't choose them at random. These positions are in what we call the first order reflection points that I was talking about before, right? So, and that is such that, you know, there is a delay path inside this network that corresponds exactly to that early reflection, okay? So by construction, right? So I'm getting something that is important in terms of perception for free like this, because it's known that early reflections are quite important to generate a certain sense of shape and size of the room. And by the way, this is just a 2D view. There is also going to be a scattering node at the top and a scattering node at the bottom. It just becomes a lot more difficult to visualize. So what does happen for the second and higher order reflection? So these blue lines correspond to an exact geometrical second order reflection, something that has Snell law, that satisfies that law that if the sound is coming from a certain direction, it's reflected specularly. Okay? So these are two examples of those second order reflections. These are not included into the network, right? That if you observe the signals here at the output of all of these delay lines, you actually don't see an echo exactly at that direction. Okay? Instead, there are some echoes, for instance, this one, that travels this way, so from the source to the scattering node to the other scattering node and at the observation point. That is close enough, right? It's more or less an approximation of it. Right? So it's going to ride by a slightly different direction with a slightly different delay, slightly different attenuation, and so on and so forth. But there is going to be an approximation of that second order reflection. And it also depends on exactly which one. So you see here this yellow path for this other second order reflection coming the other way. It's a bit coarser approximation of it. So it depends on which specific direction, which specific reflection you're talking about. And it becomes worse and worse as the number of reflections increases. But the good thing is that for high order reflections, normally we cannot really perceive the exact timing of them. So in a way, this network of delay lines, in a way, models what's more important better, and then progressively worse, the things that are less important perceptually. Okay. All right, so just don't want to go too much into the detail of this, but the operation that is carried out at the node is very similar to the one you've seen for the digital waveguide network. But we are applying also losses at the walls corresponding to wall absorption, right? Every time sound hits a boundary, there is going to be some losses that happen, thermal losses, right? So what is the energy is bounced back is not equal to the one coming in. And you need to model that in some way. So normally what you do is, like FDNs, you have something that is a unitary operation that conserves energy, but it's also followed by some losses, some wall absorption. That can also be something like frequency independent, right? Every time you pass through one of these nodes, you multiply by 0.95 to model the fact that some energy has been dispersed. Or you can also use filters for these things and model, for instance, carpet, right, which has a different frequency response from a brick wall, for instance. Okay. All right. So the fact now that you do implement those losses every time sound bounces off these scattering nodes, together with the fact that the time that it takes for a reflection to bounce off inside that network and to bounce off in a real room, they're similar. This time between average time between reflection is called mean free path, if some of you have heard the term. They're similar. So the fact that these two things are similar in the network and in the room means that what we call the reverberation time, it's a quantity that characterizes how fast the energy has decayed in a room. They're very close. So if you take a common model, so we should have probably used another model too, but if you use a common model called the image method, the geometrical acoustic model, these models corresponds quite well with this model that we call SDN. So it's the blue and the black curve. On the x-axis here you have absorption coefficient with some examples of some materials like very absorbent cotton carpet, and where the reverberation time is very low because there's a lot of absorption, and so on and so forth. And you can also use, as I said, some frequency-dependent filters, and then what we call the reverberation time also in that case is more or less well modeled. So all of these things, they come for free. Something else, it's also like, how do you model exactly the scattering operation? That means that every time something comes in from a delay line, how it's spread in the other direction, and you can do it, you have that degree of freedom in the matrix in that matrix of weights that we discussed before, and that has an effect on what we call the echo density, how it increases, but I don't want to talk about this, it's just too much detail. So one thing that is important is what is the computational complexity of this thing. So this is it's a very simple thing, right? It's just some delay lines connected onto itself. Then admittedly, like the main part of computational complexity comes from the fact that every time it comes into a scattering node, you have to carry out that matrix operation. But other than that, it's really not much, okay? And that means that this is, so on this plot you see on the x-axis that T60, right? The longer it is, of course it's, in general, if you use convolution, the more complexity you have because your impulse response needs to be longer. So on the x-axis you have T6, on the y-axis you have floating points operations per second. And the model doesn't depend on the T60, right? It just means that the delay lines become longer, right? It's still recursive because essentially you can feed directly your signal. You don't need to calculate an impulse response and then take it out. So you just, so as I say, if the room is larger, then you just increase the delay line length accordingly. On the other hand, if you use, and this is probably naive, there are better ways to do it, but if you use an FFT-based convolution, which is of course a lot faster than naive convolution, then this is order of magnitudes larger than what this model has. Okay, so and when I talk about convolution, that it's just convolution without even calculating another model, like a ray tracing model or a physical model, and so on and so forth. So this sort of structure, and it would be the same for an FDN. Okay, so this sort of structures are very fast, right? So quite appropriate for this sort of applications. One alternative interpretation of this, which is quite freaky in my mind, it's to go back to that physical model of a network of acoustic tubes. So this is a room with a source and a microphone. I just did this rendering, can't remember if in Blender or something, with the source that they're represented by these spheres, these black spheres. And this on the right is how would a network of acoustic tube corresponding to that thing that I told you before would look like. Somebody in one of the presentations I've given actually asked me if I built that, but no, I didn't. But I'm thankful that somebody thought that the rendering was good enough. So I'm going to now have you listen to it, and you should just imagine really putting a sound source here. In this case, it's going to be bongo, and then sticking your head where the other sphere is, and just listening to these acoustic tubes, what comes out of these acoustic tubes. So and hopefully you're going to see that it's not that different from a room. Okay, so I'm actually going to make a game and ask you which one do you think is the actual room and which one do you think is the network of acoustic tubes. But in general, just as a little anticipation, the reason why they sound similar is because a lot of those characteristics, perceptual feature, are similar. The mean free path, average time between one reflection and another, the T60 as a function of frequency, and so on and so forth. Okay. All right, so let me go to YouTube for a second. So this is going to show you this model, SDN, the network of acoustic tube, image method, and a physical model called finite difference time domain. And it's going to start with the anechoic sample. There is already the acoustics of this room, I'm afraid, so I can't go up without that. But this is the dry one. Okay? So I'd like you to think which one is the acoustic tubes. Okay, so very lively reverberation. There is not air absorption here. There's a number of other things. They all sound different, I'm sure you appreciate. But the question is, which one is the physical model, the one that takes a lot longer to run? So does anybody think that the network of acoustic tube was the first one? So I'm going to ask first, second, or third. Anybody thought it was the first? Okay, 1, 3, 4, 5. Don't be shy, 6, okay. How many people thought it was the second? 2, okay, 3, yeah. How many people thought it was the third? Okay, 3, 4, 5. Honestly, I can't remember which one it is, so we're just going to take a look together. So it was 6, 3, 6, right? Okay, so yeah, so 3 people got it right. The first one was the physical model, the second was the network, and the third was the geometrical acoustic one. So we can listen again if you want, just to. All right, so the bottom line, at least for us, is, okay, yeah, we can tell a difference, but we're not entirely sure which one is which, okay, which is a good sign, I suppose, right? Okay, so I'm just going to present some more results, now focusing more specifically on what we call binaural oralization, right? We want to play this back over headphones, okay? And the way that we normally do it is to render binaural sound is to take a certain number of directions, incoming directions, and then filter them by what we call head-related transfer function. And these are filters that model diffraction around the head, right? So it's a filter with 1 input, 2 outputs, 2 ears, right? It's direction dependent, of course. And they also include the delay between the 2 ears, the fact that there is a certain head shadowing at higher frequencies. So one ear is going to have a larger amplitude than the other at higher frequencies, and so on. So these are what is contained inside head-related transfer function. And on this sort of models, it's because you have a physical interpretation of where these delay lines are coming from, it's pretty easy to do this, right? Because you just pick these incoming delay lines and you filter them by HRTF filters. So, and there is a whole host of other things that we need to take care of if you heard about personalization of HRTF. But there is a lot to unpack there, but I don't want to go there. Just the part about room reverb bundled with HRTF. You can do it pretty easily here. You can also model source directivity if you want, once again, because there is a physical interpretation of these things. All right, so some people, including us, my group, have done some perceptual evaluations of these things. And this was a paper that Stoyan did, one of my bachelor students actually, published in a AES conference, I can't remember, 3 or 4 years ago, where we used this model versus FDN versus a model called cat acoustics, which is considered one of the standards for that is geometrical acoustic based that is used in the field, and a measured binaural room impulse response. So what we saw is that the SDN, so there is no statistical testing here, but trust me, it is statistically significant that there is a difference between SDN and CAT and SDN and FDN as well. What surprised us is that it was a little bit higher even than a measurement, which we're not entirely sure why it happened. So I don't fully trust everything that's came out of that comparison. I think it might be something to do about coloration, binaural correlation, that we were using the same HRTFs here, so I'm not entirely sure. But don't trust necessarily this one. I do trust the part about catacoustic and FDNs versus that model. And somebody else in another group independently implemented this model for a VR scenario that Michele Generonazzo and Stefania Serafin were one or two of the authors, if I remember correctly, in 2020. And what they tested was that effect of externalization that I talked about before. Right? So as I mentioned, you need to render room acoustics in order to feel the sound outside your head. It's been proven in the literature quite a few times. And what they saw, so on the x-axis you have different models. One is SDN, this network of acoustic tubes. The other one is a third or fourth order, higher order ambisonics measurement. And they also proposed their own personalization method. So I'm not entirely sure, don't want to go into the detail of what the difference between these two sets are. But I want you to look at this two things. And what they've shown is that, first of all, the level of externalization, this goes from 0 to 1. It's just a definition that they've given to the subjects in that case. If you don't have SDN, it's pretty low. If you include SDN with a medium-sized room, increases a lot, and then a large room increases even more. Okay, and once again, and it's also, I'm not entirely sure why it happens, but this was even higher than if you had an actual measurement based on higher order ambisonics. Okay, and this is not me, it's somebody else. So I'm just going to raise my hand and say, okay, yeah, great. We don't know exactly why it happens, but it's good. Okay. Also, there is a certain amount of, they also studied the error and the number of what we call front-back confusions. Okay, so where was I? Okay, we've also run some other perceptual experiments, also using VR, and this is one question that, I was always wondering, like, if you think about our field, people think, oh, audio, and then video, right? And the GPU on video, right? And so we wanted to look into what is the relative importance of video and audio. So we run a very simple perceptual test where we used a VR headset and we varied the video resolution of the headset from the top one, which was this was the resolution of pixel per eye, and then reduced it to 60% and then 20% of that value. And then we also changed the level of spatial audio quality, right? In one case, we had the full thing with heads, with the room acoustic models and also head tracked audio, which would change dynamically as you would move your head around. Then we removed the model, the room acoustic model, and then we made it also monaural. So in total, we had 9 combinations of these things. And then what we asked is 2 things. I'm only presenting one, which is immersion. So we asked them, how much do you feel immersed into this virtual world? There is a more elaborate definition, which I don't exactly remember, but that was the point. And that's showed on the y-axis here. And we saw something quite striking, that if you do include a room acoustic model, for instance this one, but I do think that if you include FDNs with early deflection, you're probably likely to see something similar. That essentially you have a level of immersion that is very similar to having full resolution, right? So this one, red, is 5 times less than the blue one in terms of video resolution, but it didn't have the room acoustic model. Right? So this is quite striking. So adding room acoustics increases immersion as much as increasing the video resolution 5 times. Okay, so which to me it's quite striking, and it's also testament to the fact that audio is really important in these applications, right? So if you work in a company where you have video and audio, you then need to say, look this, right? Audio is important, right? And also, I suppose we haven't calculated anything like that, but going from here to here has a very high cost in terms of video resolution. If you increase the video resolution 5 times, that is going to come at a significant cost to your GPUs. whereas adding proper reverb, yeah.
Effect called VCR salons effect.
Say again?
The VCR salons effect. It used to be the places where you can watch the videos on very, very bad
Right.
cassette.
Yeah.
But because, well, you can get actually quite decent response from the auditorium to the movie.
Right.
Because the sound is right.
Is
Once
good.
the sound
Yeah.
will deteriorate,
Yeah.
people start like, oh,
I
that's
see.
horrible.
Okay.
It's called VCR salons.
Okay. Yeah, that's very good pointer. Yeah. Yeah. Thanks. All right. So, yeah, something else that we worked on, let's see if I have time, maybe I do. It's also extending this model to coupled volumes. Because it is quite important, it's quite relevant application for this sort of applications, right? Imagine that you also, as you cross a boundary between two rooms, the transition needs to be, it's not like a sound should appear, a virtual sound should appear in the other room suddenly, right? There should be a transition between the two spaces. A student of Hussein has worked on this, and we published a paper, I think last year, on how to do this using this sort of networks. And, it wasn't as simple as we initially thought it would be, right? So Timuchin, the student who's worked on this, has worked on a number of different options. And we wanted to be able to render that double slope decay that I talked about before. And, he started by having just very simple two network connected and stuff like that. And it actually didn't work out. This version worked. We're not entirely sure if you could simplify it, but this one did work. And you need 5 of those structures to be able to model properly coupled volumes. One is the standard one that you saw. So, right, again, the signal diagram. This is the input, the output, and then this one represents that entire filter that we talked about before. Right, so that's there. And that models the sound from a source to an observation point, and this is what it's represented visually. Then you need another of these networks that models the sound that goes from the source to the aperture. Okay, so imagine that the aperture between these two volumes, it's here. So you need an SDN to model the sound from the source to the aperture. Then another one that models the sound within the second space, right? We're assuming that both source and observation point is here, which is actually the trickier bit to do for double slope decay. So you need another SDN for the other space on the other side that has both source and observation point at the aperture, right? Because it's where you're going to observe it. We're actually going to observe it on the other side. And that's this one here. Then you also need something else that connects back recursively, because you need to model now how the energy exchange happens between the two rooms. Right? As I'm speaking, some energy goes into the other space, it comes back, it's reverberated back here, and then it goes. So there is this feedback loop of connection between the two spaces, and that's why you need this other one here. And finally, you need to oralize the effect of the energy exchange between the two rooms, and that's this 5th SDN that you have on the other side that models the sound that goes from the aperture to the observation point. So, it's a little more complex than I thought initially it would be, but it turns out that this does model well that double slope decay. So this is, again, the same time on the x-axis and energy on the y-axis. And as I said before, if you have two rooms, depends on exactly how they are, but you often observe this effect where it first decays faster and then slower. And here we have this proposed model, which is called CVSDN. And then we compared it to ray tracing, and if I'm not mistaken, also to some measurements. This SM curve, I do think it's a measurement. And we saw that there is quite a good match between the two. Okay. So I'm nearly done. Another piece of work that we've done, an extension that a PhD student of mine has done, is you may imagine, okay, why do you want to stop at the first order reflection? Why scattering nodes only at the position of first order reflection? Why not a little higher, right? Why not having exact reflections up to second order and then start from there? And he studied quite a few options. I'm not going to go into all these, but in 16, this is the Duffex paper from last year. He's looked into different options. This is also work with Ochisama as well as Matteo. And then we've run some perceptual experiment, and we saw that indeed we can actually improve a little bit with respect to the original one, right? So on here we have the standard SDN, and this is the median of the standard SDN. And then you have some of these proposed higher order structure that do have an increase. We studied naturalness in this plot here. So yeah, I mean, there is more to do. There is more exciting things to come. Also, other research group have looked into this area. Stevens and others, I think VESA and other people at York were also involved in this paper. They extended this concept to model direction-dependent scattering and also outdoor scenes by adding some nodes, sky nodes that were completely absorbent. A group of Joshua Rice recently implemented it as an augmented reality framework. Published a JICE engineering report on this. Whose student of Hussein has worked on a rectangular room with diffraction, and there are a lot of other things that are happening right now that I would like to talk about, but it's better if we wait until at least some stuff it's at least been submitted. So, just to conclude, and I'm amazed that I'm to time, so there is time for some questions or some beers. But so, as I said, in general, physical room acoustic rendering provides high accuracy but computationally expensive. Some hybrid that includes early reflection, artificial reverb, or a model like XR, like SDN, they seem to be more suitable for XR applications. And yeah, we saw that these things that can improve quite a bit the sense of immersion, the naturalness of the sound. So, but without actually increasing complexity all that much. All right, thank you.